To use a histogram properly, you have to know how to put it together the right way. As a reminder, histograms describe variation in the process, and they can be used for solving various quality problems you have. They can determine process capability. They can compare data with different specifications. They can look at the shape of an overall population. So you can tell if you have skew in your data or if you have multiple averages in there. They can look at discrepancies in your data, such as gaps, and this can be seen in data like bimodal or the dog food distribution. So you have either multiple peaks in there or you have a section that's just missing. They can also be used to look at trends in your categories over time. So you can see this in plotting data during various months or years and seeing if there's any changes there. There's two different types of data that can go into your histogram. One is ungrouped, and this is used for discrete data. So if you look at the histogram on the right here, we have the number of sick days. And so this is a discrete counter because you can't have 1.5 sick days in this counting system. You can either have 1 or 2. So you get to a point where you can't divide that number any further. When you have ungrouped data, this is pretty easy to put into a histogram. You just organize the data in ascending order, like you see here, so from 0 to 10 sick days, and then you just post the frequency of each value seen here on the y-axis as number of employees to your specific bin in your histogram. And that just gives you your overall histogram shape. So this histogram has a skew. Employees have fewer number of sick days than higher number. When you get to group data, the second type of data you can have in a histogram, you start lumping values together. This will simplify your presentation, but you might lose some detail. The reason you lump the data together is because it is continuous, and that means it can be infinitely subdivided, or at least subdivided to a degree greater than what you're showing. So let's look at this histogram. We're looking at the amount spent per week on takeout in our x-axis, and so we have groups of data here. This is less than $10. So you could have spent $5.99 on your meal. You could have spent $7.50 on your meal. Both of those are less than 10, even though they're two totally different numbers. So we're putting them into one category, and that just simplifies your data presentation so you don't have basically noise coming out of your data. And then here we're looking at number of people. So we have our groups here and we can get an overall shape in our data. It looks like most people spend between $20 and $40 on their food. So we have sort of a middle average right here. Constructing histograms for ungrouped data is pretty easy. You just count up the number of observations in each group and post it. But when you have grouped data, it gets a little bit more complicated. So let's create a histogram for this pie weight data right here. Our average pie weight that we want is 45.0 ounces. We have a range of weights from 44.71 ounces right here and 45.37 ounces down here. The first thing we need to do when we're creating our histogram is determine that data range, and your range is your maximum observation minus your minimum observations. So we have 104 observations here, and our range is 0.66 ounces. Now that we've got our range, we need to figure out how many bars are going to go in our histogram, and there's a couple of different ways that you can do this. You can use Sturge's rule, where B, your number of bars, is 1 plus 0.33 times the log of n, which is your number of observations. You can use Rice's rule, which gives the number of bars as 2 times the cube root of your number of observations, or you can use the square root choice, where your number of bars is just the square root of your number of observations. So given that we have 104 observations here, Sturge's rule gives us 8 bars in our histogram. Rice's rule gives us 9, and the square root choice gives us 10. So you can imagine that our histogram is going to look slightly different based on the number of bars we have. And you have to be careful when you're presenting your data to make sure that you're giving a true look at how your data are actually organized. Regardless of what you choose for number of bars, your cell width is determined the same way. Your width is your range divided by your number of bars. And so if we use Sturgis rule, this gives us a width of 0.08 ounces. If we use Rice's rule, we have 0.073 as our width. And if we use a square root choice, we have 0.066. Now you might want to adjust your width based on your data. Sometimes it's more convenient to have a width that's a little bit different from what you're calculated, and also based on what you want your desired midpoint to be. In this example, we'll just go with the width we calculated for each one. So here again for our data, we have our range calculated, we have the number of bars, and so we want to make sure that we're properly representing our data. So if we set our midpoint around 45, we should have a good idea of the number of pies that are falling to the left of that, so underweight, and to the right of that, overweight. Here's the final grouped histogram using Sturgis rule. So we have 8 bars here. You can see our categories. We start at the lowest observation, 44.70, then we have a range, a width in our bar of 0.08, so we're going up to 0.78 there. Then we start the next bar at 44.79. And the reason we move up 0.01 is because we have observations that are 0.78, 44.78. So we want to make sure we know what category to put those in, and that's why we start the next bar at 44.79. Another thing we could also do is go out to 1 decimal point further in our cell dividers. So if we decided to go to 44.785, we could do that and then start the next one at 44.786. It just makes sorting data a little bit easier when you do that. So you want to make sure that your decimal points in your dividers are at least to the point where your data are, so you can tell which category to put your data in. So notice this general shape. It looks like we have a slightly bimodal distribution. Here's the final grouped histogram for the Rice and the square root rule. The reason it turned out like this is because we rounded our cell widths to 0.07. So 0.073 rounded down to 0.7 and 0.066 rounded up to 0.7. So in this case, our histograms look the same. And we have a similar bimodal distribution here, but notice that our shape is just a little bit different from Sturgis' rule. So you want to be careful when you're making your histograms. Look at them a couple of different ways and make sure that what you're seeing is what the data are actually telling you.